Okay, let's pick up from where we left off and conclude our discussion of the abstract data type unsorted lists, or unsorted type as it's implemented in our C++ code. And essentially we had just completed looking at the implementation that uses arrays as the underlying storage mechanism. So now what we're going to do is look at the alternative for unsorted type, which is using linked lists. We talked a little bit about linked lists, but to clarify some of the jargon, a node is typically the element that holds both the data and the pointer to the next element, the next node in the list. So a linked list is a collection of these. They're linked together using a chain of nodes that have pointers from one to the next. The big difference here in our implementations is going to be that the nodes are created as needed, and that is they are allocated dynamically in memory from the heap or the free store, as opposed to the arrays, which in our initial implementations at least were statically allocated at compile time. By default, the last node in the list has a pointer to the next node, and if it is the last node in the list, then the pointer is filled with null, and that indicates for us the last node. So here is the typical kind of drawings that you'll see for linked lists. There is some kind of what you would call the a list pointer, which is the declaration of the list itself as an entity. That is going to point at the initial node in the list. Lists can be empty, of course, that they still exist as lists, but they will have 0 elements in them, 0 nodes. However, in this case we have 4 nodes. The first one, as all of them do, have you can see in actually it's drawn in the second node. The node itself has a location, so there's a pointer to it. There's an address, that is. The info has the data that's being referred to by the node, and the second part of the struct that implements the node is going to be a pointer to the next node, in other words, another location. Lastly, you'll see at the very end there is the fourth node in the list. The next pointer is of course null, and that indicates the end of the list, and we usually show that as a slash through the address part of the node. So put item, which puts an item into our unsorted list. If the list is empty, it simply creates a new node and sets the external pointer, which is called in our case list data, to it. So very simple when it's empty. It's basically the list data is has been created, has a value of null, and then as soon as you create the first node dynamically, then you change the list data to point at that node, and you now have a list with 1 element in it. So if you follow that through, here are 4 steps. Creating a list which has 2 elements. So you would start in A. You would first create the new node that is pointed to by location. You would, in B, what you do is you update its info component to actually store the data. Then in C, you take the next pointer of the new node and you point it at the current head of the list. And then you take in D, in the bottom right hand corner, you update the list pointer itself to now point at the new node that you had just created. So now what you wind up with, oh, and by the way, I'm sorry, well, actually in this case you don't have to change the next pointer of the initial node, because by default in our case, remember this is an unsorted type, so if you're going to put new things into the list, it doesn't make any difference where you put them. So to make it easy, we're just going to always put a new thing into the first position. So whatever is there is always going to be the rest of the list. Okay, so that should be fairly clear. In terms of measuring the length, that was another one of the things in our implementation that we had to take care of. Remember, the ADT said that you should be able to ask for what the length is. If it's an array-based list, the length field has to be present, otherwise you couldn't define the size of the list inside the array. So if you allocated 10 spaces, if you didn't say length something, length 2 or length 7 or length 9, you wouldn't know exactly when to stop looking within the total allocated size of the array for the contents, the current contents, that is. On the other hand, this is a big plus for linked lists. They don't have this restriction because you're only allocating as much space as you need, and the length of the list is represented simply by the total number of nodes. So in our case, in this implementation, we could simply traverse the list and keep a running count of the total number of nodes each time. I would ask you, take a second, is this a good idea? Well, perhaps for short lists. In general, I would think, since you only need one extra int to hold the length, that it might not actually be a bad idea to also keep track, keep a running total of the length, and keep that with the list data itself, so you always know the current length. Either way, you could do it either way. In that case, put item would always increment length, and delete item, as long as the item is found and is deleted, then that would be decrementing that. The iterators that we have, remember we're talking about constructors, iterators, the mutators, etc., that we typically need for these implementations. The array-based implementation used a pointer, or a cursor, if you want to call it that, which is an array index that always says where you are in the list as you're walking along. Instead of an array index, which would be an int, the linked list here uses a pointer to a node instead, so it's an address. And then getNextItem, instead of incrementing current pos by 1, actually advances it by updating the value of current pos pointing at the next thing. Okay, so that is the next node, wherever it happens to live in memory, will be set properly. Reset list, of course, which sets you back, sets the pointer back to the beginning, simply sets it to null. Okay, and getNextItem will check if it's null and set it to the first item in the list in that case. PutItem, using our linked list implementation, creates a new node. It sets the node's info to the input data, that's what you're trying to store, sets the new node's next pointer to contents of list data, the first item in the list. Remember, in this implementation, which is unsorted, it doesn't make any difference where you put the new items, so you might as well take the easy route and always put them at the front. And then list data is set to point to the new node, and you have to be careful. Order matters in doing this. If you do step 4 before you do step 3, if you think about it for a second, you've just made the rest of the list, that is, inaccessible. Okay, you have no longer a handle on the rest of the list because you did these things out of order. So that is, of course, a memory leak. In other words, you would have lost access to all of the rest of the nodes on the list if you did this backwards. So PutItem, actually we will look at this in a little bit more detail. I'm going to have another discussion where we actually look at the code for these two alternatives. and but basically this describes what we had just gone over. So put item, if it's in an empty list, list data is, remember, is the pointer to the list. We create a new node that's location is pointing at that. We fill it with the data, that's the A. In step B, then we mark the list node that is the first one that we created with a next pointer of null, hence the slash. Then in C, we update list data to point at the node that we had just created. Voila, and a single length list. The constructor, if we start to look at the C++ implementation underneath, it's mostly unchanged. We're going to set the length to 0, and of course we have to set the external pointer, that is list data, in this implementation to null. Is full, that's another one of the operations that our ADT provides via its contract with the users. They don't have an explicit size limit, unlike the statically defined array-based lists. So new nodes can be allocated, one after another, and really the only limitation is that there's no more memory in your memory space to use, which is not likely to happen. But if you're allocating hundreds of thousands of nodes or millions or billions of nodes, and you don't have vast amounts of memory, it is conceivable that the C++ new call, which is what you use to create a new object, in our case a node struct, will throw an exception. In this case, a bad alloc exception for it couldn't do the allocation. So isFull will use what's called a try-catch block. Those are what you use to try to catch anything that might throw exceptions at runtime. And it would look a little bit, or actually it would look exactly like this in this case. We'll look at this again shortly when we talk about the code, which we're going to go over just to make sure that you understand how all these pieces fit together as C++. In this case, the Boolean isFull method is going to attempt to return true if there's no room for another one, otherwise it will. Okay, so isFull is actually attempting to do the allocation, and it will fail, but it will fail elegantly. Instead of, if you didn't do this, if you didn't use the try-catch block and you tried to do an allocation and it failed, your program would stop, it would crash. So this at least it gives you the opportunity to check first and then handle it programmatically. MakeEmpty. MakeEmpty, now this is one of the big differences between the array-based implementation and the linked list-based implementation, is that MakeEmpty has to deallocate each node one by one in order to empty the list. If you remember, in the array-based implementation, to effectively empty the list, all you had to do was set the length to 0. So effectively, you're not literally wiping out anything that is in that array. So all the data elements or whatever was in the array in your list is actually still there, but you're ignoring it. So will override it if you need to allocate the next thing or the next thing or the next thing. So essentially the big difference here is that you can't do that with a list. A list is actual memory locations all over memory as they're created, and so you actually have to step individually through them and empty them one by one. So you can use whatever looping constructor you want, while do while, repeat, whatever it is, or for, etc. The iteration would start at the head pointer, which is list data, and then walk through using the next pointer. The iteration, of course, would stop when list data is equal to null. And here's a question. What is the time complexity of this method, MakeEmpty, in this linked list implementation? The answer is, of course, it's order n. That is, it's linear because you have to traverse the whole list, whatever the whole list is. So this is, if you think about it, is one of the major distinctions between the two implementations. The array-based one, this would be constant time, and in the linked list-based version, it's order n, since you have to walk through the entire list to do this. How about get item? It's basically unchanged. You need to do a linear search because you have to, in either case, you still have to step through everything one after the other. It's unsorted, so you can't use the fact that the list is sorted to help you. So basically that's pretty much identical. The implementation, obviously, in the array-based one, you use subscripts to walk through the list. Here you need to use the pointers and follow the pointers. So here are two cases. The first case, A at the top, the data is not there. The second case, the data is there. So you can see that those values, more to search, found, and location, if you walk all the way through and you check each one starting from list data, as long as there's more to search will be true. If it's not found, it comes back false, and if location hits null, so in other words, if it's false, false, null, as you see here, you know that you've hit the end of the list and you haven't found what you were looking for. At the bottom in B, you're looking for Lila. Now we happen to know Lila is in the list, we can see it here, but algorithmically you would have to step through doing the same thing. You keep asking, is there more to search? Is this the one I'm looking for? And am I at the end of the list? So in this case, when you hit Lila, which would be the second node, there is more to search. That's true because you're not at the end. Is it found? True. Aha. And so the location, which is the cursor, the pointer that steps you through the linked list, will be the place that returns, you can return the information from. And you know that in fact it is there. Delete item is a little trickier because it requires you to update the pointer of the predecessor node, if you think about it. So the current implementation, according to the contract that the ADT for UnsortedType provides, it says that the precondition is that the item is already in the list, which in practice is probably more than you want to ask your client to have to know. So a more practical implementation, I would say, would be able to handle a case where it's not there. However, this is very simple. We're starting simple, so we're putting the onus on the client to know whether it's there or not before asking it to be deleted. So basically what you have to do in a case of delete item is to remember, if you find what you're looking for to delete, in the case of the top one, delete Lila, which happens to be the second element in the list, you have to remember that Kate was pointing at Lila, and then you have to, before you delete Lila, you have to somehow hang on to its pointer, and which is to Becca in this case, and that Lila's pointer has to then become Kate's pointer. So then after you do that, and this is what I meant about doing things in the proper order, as long as you do it in that order, then you can delete the Lila node, and Kate will now be pointing at Becca. You'll have cleaned up the memory, and the list will be one element shorter, Kate to Becca to John. In the bottom one, same idea, except the difference is that you are trying to delete the head element in the list. In that case, again, you have to remember what it was pointing at before you delete it, and in that case, the new head element, that is the thing that list data is pointing to, will be what Kate was pointing to. As soon as you update that, so you still have a handle on the rest of the list, then you can actually update memory by deleting Kate from memory. This is just as an aside in terms of C++. And this has to do with allocation, when things get allocated. That's why we bring this up here. The term lifetime means how long is a variable when you create a node or something like that, an array. How long does it have the memory assigned to it? If it's a global variable, it's basically the entire execution of the program. So it's visible also throughout the code. More interestingly is the concept of local variables. The local variable is usually only accessible inside the block that it's defined in, that is inside the curly braces, and it's only visible in that block and in any child blocks that are contained within it. If you want to have a local variable live outside of its block, then if you add the word static, that will make it live beyond its normal lifespan. And if the block exits, which would normally make the variable memory, make the variable be removed and the memory released, then static will say, no, hang on to it. And there are some cases where that actually makes sense. A dynamically allocated variable, which is somewhat different from, so for example, if you enter a method and you have something defined as, int, foo, float, money, bool, is true, those things would normally, or an array of students 100, those things, when the block exited, when the function exited, then those things would automatically be released. However, if you instead are dynamically allocating memory using the C++ new syntax, then it's your responsibility to deallocate them. Okay, so that's very important because that's another cause for memory leaks in C++. The common way to delete memory allocated as classes is using what is called the class Destructor. Of course, you have class Constructors. Those are what are called when you ask for a new something, a new object from a class that you define, let's say. Likewise, you want to be able to have them automatically be deallocated, and that's why you write a class Destructors. In that case, when the object leaves scope, it will be automatically, that is, the C++ will attempt to deallocate it for you. However, anything that you did which required the new syntax, let's say from inside of your class, that dynamic data is still hanging out there in memory. So very much like the list, where you have to do things in proper order, the destructor is designed, for example, in the case of a list, is designed to deallocate the list, the list thing itself. However, all the things inside of the list that the list created as it was being used also have to be deleted, and those things are not deleted automatically. And so that would be a big memory leak if your destructor simply was called to delete the list object itself, but didn't delete all the nodes within the list first. So the class destructor is simply a method. It's implicitly invoked. The syntax in C++ and Java is to use the same name as the class. So in unsorted list, or in our case for this implementation, with a tilde in front. The little squiggle is called a tilde. And that is your responsibility to clean up any of the memory that the class might have allocated inside of itself. So in the case of our list, of course, it's all the nodes have to be cleaned up first before the list itself is destroyed. That's an important concept. And not every language forces you to worry about these things. As I mentioned in class, Java, for example, has a built-in garbage collector, which is the information that you don't care about anymore, and it will occasionally go and reclaim all that space. It keeps track of all of these things happening. However, C++ does not do that, so you're responsible. So to wrap this up, let's look quickly at the two implementations. The array-based list is at least the way that it's defined here, which is using static arrays. Always allocates enough memory for, in our case, something called max items, which is the max number of items in any list that gets allocated. The issue with that is you might if you allocate, if max items is very large, you wind up allocating a lot of space that you might never use for your list. So on the other hand, you cannot grow it. If your max items is too small and your lists tend to be larger than that, then of course you're stuck. There's no easy way to statically well, actually, there's no way to statically allocate an array like this. You would have to come up with something like a hybrid array-based implementation, which instead of, let's say you statically defined a list to begin with as an array, and then if you, when you're keeping track of things, if somebody asked you for a list that was one element larger than that, then you could do something like dynamically allocate another array in memory, which you can do using the new pointers, and then perhaps copy over everything from the original array into the new array and then delete the original array. But of course now we're talking about something different. Now we're talking about dynamic arrays instead of statically defined arrays. The example we have here is the simplest version, which is simply to, at compile time, allocate enough memory for X things, or max items in our case. The linked list implementation only occupies enough memory for the items in the list as they're allocated. So in that sense, it's much more efficient in terms of just pure memory usage. However, the trade-off, and as you'll learn throughout this class, there are always trade-offs between alternatives. You have to traverse the entire list for some of the operations. On the other hand, because the array is fixed in memory, then you can, and it's traversed essentially by the subscript value, that allows you to randomly jump around in it and not have to follow pointers the way that the list does. That distinction is going to become important when we talk about the sorted arrays and the implementations versus the linked list implementations of the sorted lists, because essentially with the array implementation of a sorted list you can do a binary search, and binary search, as we mentioned in class, is, instead of being an order n kind of operation, is an order log n, and that is always a big win if you compare two sets of operations. So to wrap this up, just to look at the comparison, here's a chart that shows some of this. Many cases, both of the methods that are operations for this ADT are constant time, that's the O1. However, in some cases, as you might think, put item is also order 1, because and the only reason we can make this assertion is the list is not sorted, so we're always going to put it in the first position, so there's no traversing of the list. The list could be 100 or 1,000 or 10,000 long, and we always have a constant time insertion here. However, delete item is going to be order n, because of course the delete item implies that you have to find it first before you can delete it. So those are, you might say, well, this is pretty much the same. However, at least in one case, there is the distinction that points up the major distinction between an array implementation and a linked list implementation. That is the fact that in some cases you're going to have, at least in an unsorted list as we have here, are going to have to traverse the entire list to do some of these functions. And so there's one of the trade-offs that you always have between these kinds of alternatives. The arrays are more fixed in memory, so they're less dynamic. They don't grow or shrink without some finagling to make them grow or shrink. That's not their nature, versus the linked implementation, which can grow and shrink at will. However, in order to find things, and find is actually the basis, or search is actually the basis for many other operations. If you look at the bottom of the chart, put item and delete item, the very first thing they both have to do is find. So that, and it depends upon the operation you're doing, but that is one of the distinctions you'll find between the two implementations. So that will wrap up our discussion of unsorted lists. The sorted list discussion is should be very fast, because it's essentially the same with the twist that we now have to keep the list elements in some sort of an order based upon a key that we define has a comparison function for, and so that you can always ask the question, is this key value less than, greater than, or equal to another value that we're looking for? So that will allow us then to store things in sorted order, and once they're in sorted order, it allows us to do other things like binary search, which as I said, will give us much faster implementations since they are log based instead, which we'll see in more detail. So that's it. We'll pick this up again when we talk about the sorted type.